The metal treads of the captured Sherman tank bit into the soft earth of the proving ground as Lieutenant Takeshi Yamamoto watched it roll to a stop. The morning of November 7th, 1943, had dawned cold and clear outside Tokyo, and the air carried that peculiar smell of diesel fuel mixed with gun oil that hung around military testing facilities. Yamamoto had been summoned here 3 days earlier with orders that offered no explanation, only a location and a time. Now, standing beside this olive-drab monster that still bore scorch marks from whatever battle had disabled it in the Solomon Islands, he understood why the summons had come from the General Staff itself. The High Command needed answers. They needed to understand why their Type 97 Kihar tanks machines that had swept through China and Malaya with such apparent invincibility were being systematically destroyed by these American vehicles at a rate that made no tactical sense. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Yamamoto had spent the previous week living inside this captured Sherman. Every centimeter of armor plate, every mechanical linkage, every component of the suspension and drivetrain had passed under his scrutiny. He had measured the armor thickness with calipers 51 millimeters on the frontal arc, sloped at 56 degrees. He had studied the vertical volute spring suspension, noting how each bogie assembly was designed to absorb terrain irregularities. He had examined the 75mm M3 gun, calculated its muzzle velocity, analyzed the ammunition types found in the ready racks. On paper, the Sherman was a competent design, well armored by Pacific Theater standards, adequately armed, reasonably mobile. Nothing about it suggested the kind of battlefield dominance that reports from Tarawa, Bougainville, and New Guinea described. Those reports haunted Yamamoto. They spoke of American tanks firing accurately while advancing at speed. Tanks that never stopped moving, never presented a stationary target, yet somehow struck Japanese defensive positions with devastating precision. The reports came from multiple sources, surviving tank commanders, infantry officers who had witnessed the engagements, even a naval observer who had watched Sherman tanks drive off landing craft at Tarawa and immediately engage bunkers while still wading through chest-deep surf. Every report described the same impossible phenomenon: continuous, accurate fire from moving platforms. Yamamoto's training at the cavalry school in Chiba had been thorough, and he had believed comprehensive. The fundamental principle of armored gunnery was simple, universal, and grounded in basic physics. A tank gun several hundred kilograms of steel, mounted on a platform weighing dozens of tons, moving across uneven terrain could not hit anything while in motion. The gyroscopic effects of the vehicle's movement, the constant pitching and rolling of the suspension, the vibration from the engine and tracks, the gunner's inability to maintain a stable sight picture, all these factors combined to make accurate gunnery from a moving tank effectively impossible. Every army in the world designed its armor tactics around this fundamental truth. German panzer crews in North Africa, Soviet tank brigades in the vastness of Russia, British armor in the Western Desert, they all operated on the same principle: find a firing position, halt, aim, fire. Then reposition before enemy counterfire could bracket your location. The Type 97 Kihar embodied this doctrine perfectly. Its 57mm Type 97 gun was mounted rigidly to the turret ring. The gunner traversed the turret using a hand crank, elevated the gun with another manual control, and fired only when the tank commander confirmed a stable platform. The tank's armor might be thin, just 25mm on the frontal arc, but Japanese armor philosophy had consciously chosen mobility and reliability over heavy protection. The Kihar weighed only 15 tons, making it suitable for the poor roads, weak bridges, and soft ground conditions throughout Asia and the Pacific Islands. Its air-cooled diesel engine was less powerful than liquid-cooled designs, but far more reliable in tropical conditions, where clean water was scarce. The tank had been optimized for the infantry support role that Japanese strategists considered most important. Advance with infantry, halt at key positions, deliver accurate suppressive fire against enemy strongpoints, then advance again. This philosophy had proven devastatingly effective in China. From 1937 through the early war years, the Chiha had terrorized Chinese defensive lines. Chinese forces lacked effective anti-tank weapons. Their best option was often a brave soldier with a bundle of hand grenades trying to get close enough to disable a track. Against such opposition, the Chiha's combination of speed and firepower was overwhelming. The tank's 57mm gun could penetrate most fortifications at combat ranges, and its two Type 97 machine guns suppressed infantry attempting to approach with close assault weapons. The armor might be thin, but it mattered little when facing enemy forces equipped primarily with rifles, machine guns, and occasional light artillery. When Japan struck south into Malaya and the Philippines in December of 1941, the same tactics worked brilliantly. British forces in Malaya possessed few tanks and only limited anti-tank capability. American forces in the Philippines were even less prepared for armored warfare. The Chiha seemed invincible to soldiers who had never faced armor before, and Japanese tank crews won engagement after engagement using the halt-fire-move doctrine they had, perfected in China. But something had changed in the jungles and coral atolls of the Pacific after mid-1942. The Americans had begun landing tanks first in small numbers at Guadalcanal, then in increasing quantities as their industrial production reached full capacity. And these American tanks, particularly the M4 Sherman, were destroying Japanese armor at ratios that made Yamamoto's instructors' tactical calculations meaningless. Captain Sato, the senior armor officer overseeing today's test, had combat experience that lent weight to his observations. Sato had commanded a tank company on Guadalcanal and had survived an encounter with American armor, a rare distinction, since most Japanese tankers who met Shermans in battle did not survive to file reports. I watched them drive through our defensive lines. Sato had told Yamamoto the previous evening, his voice carrying the flat effect of a man recounting trauma. We had prepared positions in depth, anti-tank guns, pre-registered on likely approach routes, Chiha tanks in hull-down positions with excellent fields of fire. Everything according to doctrine. The Marines landed their Shermans at dawn, and by noon our entire defensive system had collapsed. Sato described watching a Sherman advance directly toward his position, its gun firing continuously. At first, I thought they were simply spraying fire for psychological effect, accepting poor accuracy in exchange for suppressing our return fire. But then I noticed their rounds were hitting. Every third or fourth shot struck a bunker, an anti-tank gun position, a fighting hole, and the tank never stopped moving, never gave our gunners a stationary target, never paused to allow accurate return fire. Sato had ordered his own Chiha tanks to counterattack. They had maneuvered toward the advancing Shermans using proper doctrine, moving rapidly between covered positions, halting behind terrain features, firing at the American tanks, then repositioning before counterfire could arrive. The first Chiha stopped behind a coral ridge. Its commander selected a target, a Sherman advancing 400 meters distant, and ordered fire. The 57mm round struck the Sherman's frontal armor at a poor angle and ricocheted away, leaving only a bright scar on the armor plate. The Chiha's gunner loaded another round, adjusted his aim, prepared to fire again. And then the Sherman's gun spoke. The 75mm armor-piercing round penetrated the Chiha's thin frontal armor, passed through the fighting compartment, and ignited the ammunition storage. The Chiha burned. The second tank tried the same maneuver, Sato continued. Same result. The Sherman was moving, I could see it clearly, advancing at perhaps 10 or 15 kilometers per hour, but its gun fired, and my tank died. By the time the third Chiha reached a firing position, the crew's morale had broken. They fired one hasty shot that missed by 20 meters, then tried to retreat. The Sherman destroyed them while they were moving. A moving target hitting another moving target. It shouldn't have been possible. Sato had survived only because his command tank had been positioned further back, coordinating the company's movements. He watched the entire engagement from relative safety, watched 3 Chiha tanks destroyed in less than 5 minutes by a single Sherman that never stopped moving and never missed. The after-action report he filed had been detailed, precise, and professionally written. The General Staff had sent it back with annotations suggesting that Sato had misremembered the engagement, that stress and the chaos of combat had distorted his perception. Surely the American tank had paused to fire. Surely multiple Shermans had been present, creating the illusion of continuous fire. Surely the Japanese crews had been inadequately trained or had panicked. But Sato knew what he had seen, and now, standing on this proving ground with a captured Sherman available for testing, he would prove it. The test protocol was straightforward. A Type 97 Chiha would make firing runs against stationary targets at various speeds, 5 km per hour, 10 km per hour, and 15 km per hour. These were standard combat speeds for an advancing tank, slow enough to maintain some engine noise discipline, fast enough to close with enemy positions before they could adjust fires or reinforce. The Chiha would fire at target arrays positioned at 400, 600, and 800 meters, typical engagement ranges for Pacific theater combat, where thick jungle or rough coral terrain usually prevented longer-range gunnery. Then the Sherman would make identical runs, same speeds, same ranges, same target arrays, every variable controlled except the tank itself. The results would be documented by multiple observers with stopwatches and range-finding equipment, photographed for the record, and analyzed by officers from the armor school. If the Sherman could really fire accurately while moving, the test would prove it beyond doubt. If the Pacific combat reports had been exaggerated or misunderstood, the test would reveal that too. The target arrays represented typical Japanese defensive positions, reinforced machine gun bunkers, anti-tank gun emplacements, infantry fighting positions, observation posts. Each target was constructed to scale, using similar materials to what Japanese engineers would employ in actual defensive works. Wooden frames represented structural elements, sandbags simulated earth and log fortifications, painted canvas sheets stood in for camouflage netting. The targets weren't designed to be destroyed that would make it impossible to assess shot placement, but rather to register hits. Each target had been whitewashed, so that shell impacts would leave clear dark marks on the white surface, allowing observers to measure accuracy. The morning air carried a bite that reminded Yamamoto of early winter in northern Honshu, where he had grown up. The proving ground had been agricultural land before the war, rice paddies and vegetable plots, worked by farming families for generations. Now the fields had been converted to military use, the irrigation channels filled in, the soil compacted by tracked vehicles. Wooden observation towers flanked the range, giving staff officers elevated positions from which to watch the tests. A small group of senior officers had arrived from Tokyo specifically for this demonstration. Their presence added weight to the proceedings. This wasn't a routine technical evaluation. This was the General Staff seeking answers to a problem that threatened to undermine Japanese armor doctrine. The Chiha crew climbed into their tank. Yamamoto knew these men. They were instructors from the armor school, hand-picked for their exceptional skill. If any Japanese tankers could achieve accurate fire from a moving platform, these men could. The tank's engine coughed to life, the air-cooled diesel settling into a steady rhythm. The commander's head and shoulders were visible in the open turret hatch, his goggles pulled down against the dust. He gave the ready signal. The Chiha began its first run. 5 km per hour, barely faster than a walking pace. The tank rolled forward smoothly, its suspension absorbing the minor irregularities in the proving ground surface. At 400 meters from the first target array, the gun fired. The 57mm report was sharp and clear in the morning air. Yamamoto watched through binoculars as dust kicked up perhaps 1.5 meters behind the first target. A clean miss. The gunner was compensating for the vehicle's movement, trying to predict how the hull's motion would affect his aim at the moment the gun fired. But the calculation was imperfect. The gun fired again. This time the round struck the target frame, but several feet to the left of center mass. Tactically, it might have been close enough to suppress or wound defenders, but it wasn't the kind of precision hit that would destroy a fortified position. A third shot followed. This one struck dead center. The gunner had found his rhythm, adjusted for the tank's motion, and delivered an accurate round. But it had taken 3 shots to achieve one good hit at 5 km/h against a stationary target at 400 meters. The Chi-Ha continued its run, engaging the 600-meter and 800-meter target arrays. At 600 meters, moving at 5 km/h, the tank achieved 2 hits out of 5 rounds fired. At 800 meters, the accuracy degraded further: 1 definite hit, 1 near miss that might have had tactical effect, and 3 clean misses. Overall performance, acceptable, but not impressive. The gunner was fighting the tank's motion with every shot, trying to time his trigger pull for the brief moment when the gun might be aligned with the target, knowing that the hull's pitching and rolling made such moments rare and unpredictable. The second run began. 10 km/h, a realistic combat advance speed, fast enough to close with enemy positions quickly, but not so fast that the tank became difficult to control on rough terrain. The Chi-Ha accelerated, its tracks churning the packed earth. At 400 meters, the gun fired. The round impacted 3 meters to the right of the target. The gunner fired again. This round fell short by 2 meters. A third shot went high. Yamamoto lowered his binoculars and glanced at Captain Sato. The senior officer's expression was carefully neutral, but his jaw was tight. They were watching skilled, experienced gunners struggle to hit stationary targets at moderate range while moving at what tankers considered a slow speed. The Chi-Ha's suspension, designed for reliability and ease of maintenance rather than stability, transmitted every bump and irregularity directly into the hull. The gun, rigidly mounted to the turret, moved with that hull up and down, side to side, following every motion of the vehicle beneath it. The gunner, peering through his telescopic sight, watched the target bounce and shake in his field of view, trying to anticipate where the target would be in the fraction of a second between deciding to fire and the gun actually discharging. At 600 meters, moving at 10 km/h, the Chi-Ha achieved 1 marginal hit out of 5 rounds fired. The other 4 rounds scattered in a pattern covering roughly 50 meters of frontage area fire at best, the kind of shooting that might suppress unprotected infantry but would do nothing against fortified positions. At 800 meters, the gunner gave up trying for precision and simply fired in the general direction of the targets. Not a single round struck close enough to matter. The final run was almost painful to watch. 15 km/h, maximum practical combat speed on good ground. The Chi-Ha accelerated to this speed and began its firing run. The tank's motion became pronounced, the suspension working hard to absorb terrain features at this velocity. Through his binoculars, Yamamoto could see the gun barrel rising and falling, sweeping side to side as the hull beneath it pitched and yawed. The gunner fired 6 rounds during the run. Not one came close to any target. The rounds impacted in a spread pattern that would have been ineffective against anything except perhaps massed infantry in the open. The tank commander ordered a halt. The Chi-Ha's tracks locked, the hull settled onto its suspension, and the vehicle became motionless. The gun fired twice more at the 600-meter targets. Both rounds struck home with precision. The demonstration was complete, and its message was clear. Japanese armor doctrine was correct. Tanks that wanted to hit their targets needed to stop first. Then came the Shermans. In turn, and everything Yamamoto thought he understood about armored gunnery collapsed. The American tank was larger than the Chiha, longer, wider, considerably heavier at 30 tons. Yet when its engine started, the sound was different, deeper, more powerful, but also smoother. The Continental R975 radial aircraft engine that powered the Sherman produced 400 horsepower, nearly double the Chiha's output. But power wasn't what caught Yamamoto's attention. It was how the tank moved. The Sherman rolled forward, and its motion had a quality the Chiha lacked. The suspension, those vertical volute springs supporting each bogie assembly, seemed to actively dampen the terrain's effect on the hull. The tank didn't just absorb bumps, it seemed to smooth them out, to maintain a more level platform despite the ground passing beneath its tracks. Yamamoto had examined the suspension closely during his week of study, but seeing it in motion revealed characteristics that static analysis couldn't capture. The tank accelerated to 5 kilometers per hour and approached the 400-meter target line. The turret rotated slightly, the long 75mm gun tracking onto the first target. Then Yamamoto heard a sound he couldn't immediately identify. A high-pitched whine, like an electric motor running at high speed, overlaying the deeper rumble of the engine. The sound seemed to be coming from the turret itself. The gun fired. The target disintegrated, not just marked by a hit, but actually destroyed by the impact of the 75mm high-explosive round. 3 seconds later, the gun fired again. Another target shattered. The Sherman maintained absolutely constant speed. No pause, no hesitation, no moment of vulnerability. Just continuous forward motion and devastating accurate fire. Yamamoto felt something cold and heavy settle into his stomach. He raised his binoculars, focusing on the Sherman's gun barrel. The tank was moving. He could see the hull rising and falling slightly as the suspension worked, could see the tracks churning dirt. But the gun barrel itself remained remarkably stable. Not perfectly level, no mechanical system could achieve that, but stable enough. As if the gun was somehow partially independent of the hull's motion, compensating for the vehicle's pitch and roll, staying pointed at the target even as the platform carrying it moved across uneven ground. 5 rounds fired during the first run. 5 targets ceased to exist. The Sherman never slowed, never paused, never gave a hypothetical defender more than 3 or 4 seconds between shots. Any Japanese anti-tank gun crew trying to engage this tank would have to identify the threat, traverse their gun, aim, and fire all within that tiny window, and they'd be aiming at a moving target while taking accurate fire in return. Again, Captain Sato said quietly. His voice was carefully controlled, but Yamamoto could hear the tension beneath words. 10 kilometers per hour, 600-meter targets. The Sherman accelerated. The whining sound from the turret grew slightly louder. Yamamoto suddenly understood that sound was connected to whatever system was keeping the gun stable. Some kind of motor, constantly adjusting, compensating, keeping the gun pointed at its target despite the vehicle's movement. The tank reached 10 kilometers per hour and began its run. The gun fired. A machine gun bunker target exploded into fragments. The turret traversed slightly right. Another shot, another target destroyed. The Sherman was moving at twice the speed the Chiha had struggled with, engaging targets at longer range and hitting with methodical, mechanical precision. This wasn't luck. This wasn't exceptional gunnery skill. This was a system, a technological solution to the fundamental problem of tank gunnery that every other nation had simply accepted as unsolvable. 6 rounds fired during the 10-kilometer-per-hour run. 6 targets destroyed. The Sherman's commander hadn't even needed to slow down for the longer-range shots. The system, whatever it was, compensated for speed, range, and terrain with equal effectiveness. Yamamoto thought about Japanese tank crews who would face this machine in combat. They would maneuver for position, halt their tanks, aim carefully, and fire. If they hit, The Sherman's thick armor would likely deflect their 57mm rounds unless the angle and range were perfect. If they missed, they'd need to reload and aim again, and during those precious seconds, the Sherman would be advancing, closing range, firing continuously with accuracy no Japanese tanker could match. 15 kilometers per hour, Sato ordered. 800-meter targets. This was the test that mattered. 15 kilometers per hour was fast enough that no doctrine, no training, no amount of skill should allow accurate gunnery. The Chiha had been effectively blind at this speed, its gunner unable to even approximate target engagement. If the Sherman could hit targets at 800 meters while moving at 15 kilometers per hour, then something fundamental about armored warfare had changed. The Sherman's engine roared as the tank accelerated. The whining from the turret became a constant presence beneath the engine note. The tank reached 15 kilometers per hour fast enough that infantry would struggle to keep pace, fast enough that the suspension was working hard to maintain stability. Through his binoculars, Yamamoto watched the gun barrel. It was moving slightly, rising and falling in small oscillations as the system tried to compensate for the vehicle's motion. But those oscillations were measured in degrees, not in the wild swings that affected the Chiha's uncompensated gun. The gun fired. 800 meters away, a target marking an infantry fighting position erupted in splinters and dust. The gun fired again 4 seconds later. Another hit. The Sherman was moving fast enough that its own dust trail partially obscured it from observation. It was moving faster than most tactical situations would require, at ranges where many tank versus tank engagements historically occurred, and it was hitting. 8 rounds fired during the high-speed run. 7 struck their intended targets. 1 missed the shell, impacted approximately 2 meters to the left of a target, close enough to potentially damage or suppress the position, but not a direct hit. Still, 7 out of 8 at 800 meters while moving at 15 kilometers per hour represented accuracy that should have been impossible. The Sherman rolled to a stop. The turret rotated to face the observation tower where Yamamoto and the other officers stood. For a long moment, no one spoke. The sound of the Sherman's engine idling seemed very loud in the silence. Then Captain Sato turned to his aide. "Bring Lieutenant Nakamura here. I want to hear from the crew." Lieutenant Nakamura was the Japanese officer who had been trained to operate captured enemy equipment, a necessary specialty as the war progressed, and more American vehicles fell into Japanese hands, either through battlefield capture or recovery operations after engagements. Nakamura emerged from the Sherman's turret hatch, his face flushed from the heat inside the tank, but his expression one of barely contained excitement. Nakamura said as he approached the observation tower, "I have never experienced anything like this. The system, they call it a gyro stabilizer. It keeps the gun on target regardless of vehicle motion. There's a gyroscope, spinning at high speed, connected to electric motors and hydraulic actuators. When the tank pitches forward, the system automatically adjusts the gun's elevation to compensate. When the hull rolls, the system corrects. The gunner simply tracks the target laterally and decides when to fire. The vertical compensation is automatic." Yamamoto felt as though someone had just explained that the Americans had developed a method for violating physical laws. "Show me," he said. They climbed onto the Sherman's deck and dropped through the turret hatch into the fighting compartment. The interior was cramped. American tankers were evidently larger men than their Japanese counterparts, but everything was laid out with impressive logic. The gunner's position featured a powered traverse mechanism that put the Kaiha's manual hand crank to shame. A foot pedal controlled the traverse rate, allowing fine or coarse adjustment with minimal effort. The gun sight was well designed, with clear optics and logical markings, but the critical component sat beside the gun mount. A steel housing, roughly the size of a small suitcase, was bolted to the turret floor and connected to the gun's elevation mechanism through a series of mechanical linkages. Thick cables ran from this housing to a motor generator set mounted lower in the hull. Small placards in English marked various controls and indicators. One switch, prominently placed on the gunner's control panel, read "Stabilizer on/off." "This is the gyro stabilizer system," Nakamura explained, pointing to the steel housing. "Inside is a gyroscope, a wheel spinning at very high speed, maintained by an electric motor. The gyroscope's axis is aligned with the gun's elevation axis. When the tank pitches, when the hull nose drops or rises, the gyroscope maintains its orientation. This creates a mechanical error signal that drives this amplitude motor." He indicated a smaller housing connected by more cables, which then powers a hydraulic actuator that corrects the gun's elevation. Yamamoto had read about gyroscopes. Aircraft used gyroscopic instruments for attitude indication. Naval vessels used gyro compasses for navigation. Torpedoes used gyroscopic guidance. The principle wasn't mysterious. A rapidly spinning mass resists changes to its orientation, providing a stable reference, even when the platform carrying it moves. But applying that principle to stabilize a tank gun, creating a system robust enough to operate reliably in combat conditions, building it small enough and light enough to fit in a tank turret that required engineering sophistication he hadn't imagined possible. "May I try it?" Yamamoto asked. Nakamura nodded and moved aside. Yamamoto squeezed into the gunner's position, familiarizing himself with the controls. The foot pedal for powered traverse, the elevation hand wheel, though he noticed this was connected to the stabilizer system rather than directly to the gun. The trigger, a simple button on the traversing hand grip, and the stabilizer switch, currently in the off position. He flipped the switch to on. Immediately, he felt a subtle change. A slight vibration transmitted through the gun controls, accompanied by that high-pitched whine he'd heard from outside the gyroscope, spinning up to operating speed. Through the gun sight, he selected a target 600 meters distant. The sight picture was clear, the target centered in his field of view. "Driver," he called down through the intercom system, "advance at 10 kilometers per hour." The Sherman's engine note changed as the driver engaged the transmission. The tank began moving forward, and Yamamoto watched through the gun sight as the target began to bounce and shake in his field of view. But the movement was surprisingly limited. The crosshairs oscillated around the target in small, regular patterns, but they didn't sweep wildly across the landscape the way they would in a Chi-Ha. The system was working, he could feel it through the gun controls. Tiny automatic adjustments happening continuously, faster than any human reflexes could manage. He centered the crosshairs as well as he could and pressed the trigger. The gun fired, the recoil absorbed by the mount's hydraulic buffer. Through the gun sight, he saw the target shatter, a hit, first round while moving at combat speed. It felt like cheating. It felt like someone had secretly rewritten the rules of warfare without informing the Japanese general staff. Every tactical manual, every training exercise, every combat doctrine developed over years of armor warfare experience, all were predicated on the assumption that accurate fire required a stationary platform. The Americans had simply eliminated that requirement. They had looked at the same problem every other nation accepted as unsolvable and engineered it away. Yamamoto climbed out of the Sherman and stood on the proving ground, trying to process what he had just experienced. The cold morning air did nothing to clear the confusion in his mind. This wasn't a marginal improvement in gunnery capability. This wasn't a matter of better training or superior tactics. This was a fundamental shift in what tanks could do. A Japanese tank crew could be brave, skilled, and tactically brilliant, could execute their doctrine flawlessly and still die because their equipment lacked a system that kept the gun pointed at targets while the vehicle moved. Captain Sato had gathered the test observers in a small briefing room at the edge of the proving ground. Maps covered one wall, technical diagrams covered another. A sergeant was compiling the test data, shot counts, hit percentages, speed measurements, range calculations. The numbers told a story that no amount of Japanese fighting spirit could rewrite. At 5 kilometers per hour, The Chiha had achieved approximately 50% accuracy against stationary targets at 400 meters. The Sherman had achieved 100% accuracy at the same speed and range. At 10 kilometers per hour, the Chiha's accuracy had dropped to roughly 20%. The Sherman maintained 85% accuracy. At 15 kilometers per hour, the speed where the Chiha effectively couldn't hit anything, the Sherman still achieved nearly 90% accuracy. These results explain every combat report we've received from the Pacific, Sato said quietly. The room had gone silent as officers studied the data. Our tank crews are not cowards. They are not incompetent. They are not failing to execute doctrine. They are facing an enemy with a technological capability we cannot match. One of the senior officers from Tokyo, a colonel whose uniform bore campaign ribbons from China and Malaya, spoke up. Can we replicate this system? Can our engineers develop an equivalent stabilizer for the Chiha or for newer designs? Sato looked at Yamamoto, who had spent more time examining the Sherman's systems than anyone else present. Yamamoto chose his words carefully. Sir, I have consulted with engineers from the Technical Bureau. The gyro stabilizer system requires manufacturing precision far beyond our current industrial capabilities. The gyroscope itself must be balanced to tolerances measured in microns, thousands of a millimeter. The bearings that support the spinning gyroscope must be manufactured to equally exacting standards, or friction and vibration will destroy accuracy. The Ampledyne motor that drives the correction system requires specialized electrical steel and precision windings. The hydraulic actuators need seals capable of withstanding high pressures without leaking, even after thousands of hours of operation in conditions of extreme vibration and temperature variation. He paused, making sure his next words were understood clearly. Each of these components individually stretches our manufacturing capability. The system as a whole, with all components working together reliably in combat conditions after being transported across oceans and subjected to rough handling, is beyond what our industry can currently produce. The Americans built this system because they possess an industrial base capable of precision manufacturing at scale. We do not. The silence that followed was profound. This wasn't a question of will or courage or tactical innovation. This was industrial capacity translated directly into battlefield advantage. Japan had entered the war with military equipment adequate for the conditions it expected to face, equipment optimized for China, for Malaya, for campaigns against enemies who lacked modern armor. But the Americans possessed not just greater numbers, but fundamentally superior technology, built by an industrial system capable of producing precision components that Japanese factories couldn't replicate. The colonel from Tokyo asked the question that mattered most. If we cannot match this technology, what do we do? Sato's response was measured but grim. We adapt. We revise our armor doctrine to account for enemy capabilities we cannot duplicate. We train tank crews in ambush tactics that minimize exposure time. We position anti-tank guns at longer ranges and accept lower accuracy in exchange for engaging Shermans before they close to their optimal range. We issue more close assault anti-tank weapons to infantry and train them in desperate close-range attacks. He paused. None of these adaptations change the fundamental equation. A tank that must halt to fire will always be at a disadvantage against a tank that can fire while moving. The briefing continued through the afternoon as officers drafted their report to the General Staff. Yamamoto contributed technical details, verified measurements, precise descriptions of the stabilizer system's operation, but his mind kept returning to a simple, devastating thought. Somewhere in America, factories were producing these gyro stabilizers by the hundreds, perhaps by the thousands. Training facilities were teaching Sherman crews how to use them. Logistics systems were delivering them across the Pacific. And Japanese soldiers, men like those he had trained with, friends from the cavalry school, crews who had studied the same doctrine he had learned, were dying because their equipment couldn't compete. The report took shape over several days of writing, revision, and review. It documented the test results in exhaustive detail range tables, showing accuracy versus speed, photographs of target impacts, technical drawings of the stabilizer system copied from American maintenance manuals found in the captured tank. The engineering section explained the gyro stabilizer's operating principles, the mechanical and electrical components required, and the manufacturing tolerances necessary for reliable operation. The tactical analysis section drew conclusions that must have been painful for senior officers to read. Japanese armor doctrine. The report stated in language carefully chosen to avoid direct criticism of the general staff was developed for conditions that no longer exist. Our tanks were designed and our crews were trained for combat against enemies who lacked modern armor or effective anti-tank weapons. Against such opponents, the Type 97 Chiha's combination of mobility, reliability, and adequate firepower proved highly effective. However, American forces possess both superior armor and technological capabilities that fundamentally change the nature of tank warfare. The report made specific recommendations. Existing Chiha tanks should be up-armored if possible, even at the cost of reduced mobility. The added weight would make the tanks slower, but a tank that survived to reach firing position was more valuable than a fast tank that was destroyed while maneuvering. Tank crews should be trained in defensive ambush tactics, selecting positions with excellent concealment, pre-ranging key terrain features, planning rapid repositioning routes. The goal should be to get the first shot, make it count, and then relocate before American counterfire arrived. Anti-tank gun crews received special emphasis in the recommendations. They should be equipped with the longest range weapons available and trained specifically in engaging moving targets. Yes, hitting a moving Sherman at 800 or 1,000 meters was difficult, but it was still possible, and engagement at those ranges gave Japanese gunners a chance to destroy the Sherman before it closed to its optimal range where the stabilizer system provided maximum advantage. Better to take a difficult long-range shot than to wait for a closer, easier shot that would never come, because the Sherman would destroy the gun position first. Infantry would need more close-range anti-tank weapons, magnetic mines, satchel charges, lunge mines for suicide attacks. These weapons were last resort measures, requiring incredible courage to employ, but against an enemy who could fire accurately while moving, they might be the only option. The report acknowledged, without stating it explicitly, that these recommendations amounted to asking infantry to sacrifice themselves because Japanese armor couldn't match American technology. The report concluded with an assessment that was pertinent, simultaneously honest and hopeless. The gyro stabilizer system provides American armor with a decisive tactical advantage that Japanese forces cannot currently counter through improvements in doctrine, training, or fighting spirit. This advantage is fundamentally technological and can only be addressed through equivalent technological development or through accepting tactical adaptations that will result in significantly higher casualties for Japanese forces. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The report was classified top secret and distributed to a carefully limited list of senior officers and technical staff. Yamamoto heard later that reactions had varied widely. Some officers dismissed the findings as defeatist, arguing that Japanese courage and tactical skill would overcome any technological disadvantage. Others recognized the implications immediately and began the difficult work of revising training programs and tactical doctrine. A few, very few, grasped the broader strategic truth the report implied. If America could produce sophisticated gyro stabilizers for tanks, what other technological advantages might they possess? By mid-1944, when the report's recommendations began filtering down to frontline units, the tactical situation had deteriorated so rapidly that doctrinal innovations could no longer change outcomes. American forces were island hopping across the Pacific, and every landing brought more Shermans. The tanks that had seemed so formidable to Japanese observers were being supplemented by improved models, Shermans with better armor, more powerful guns, even more sophisticated fire control systems. And behind those Shermans came an endless tide of supplies, ammunition, replacement parts, and fresh crews. Yamamoto spent the latter part of 1944 and early 1945 training new tank crews. The men were increasingly young, many barely out of school, rushed through abbreviated training programs as Japan's pool of experienced soldiers dwindled. He taught them the doctrine: maneuver carefully, use terrain for protection, select good firing positions, halt the tank completely before firing, to make the first shot count because there might not be time for a second. He did not tell them about the gyro stabilizer. What purpose would it serve? They couldn't change the equipment they'd been issued. They couldn't manufacture precision components that Japan's strained industrial base couldn't produce. They could only fight with the tanks they had, using tactics that were obsolete before they learned them, against an enemy whose technological advantages grew more pronounced with each passing month. Sometimes, late in the evening after training had concluded, Yamamoto would think about that morning at the proving ground. The sound of the Sherman's gyro stabilizer winding up the high-pitched whine that preceded devastatingly accurate fire, the sight of the gun barrel staying level despite the hull's motion, as if some invisible hand was compensating for every bump and pitch. The cold realization that Japan was fighting an enemy who possessed not just numerical superiority but qualitative advantages that Japanese industry couldn't replicate. The gyro stabilizer was just one system in one type of tank, but it represented something larger and more ominous. A nation with the industrial sophistication to implement complex, precision-engineered solutions to tactical problems. A nation that could manufacture components requiring micron-level tolerances, assemble them into reliable systems, and produce those systems by the thousands. A nation that had thought deeply about the practical problems of armored warfare and solved them with engineering rather than exhortations to courage. Japanese engineers did attempt to develop stabilizer systems for experimental tank designs late in the war. These systems were crude compared to the American gyro stabilizer simple mechanical linkages that provided minimal compensation rather than sophisticated gyroscopic control. The experimental tanks that received these systems performed marginally better than unmodified vehicles, but nowhere near Sherman capability. And the systems proved unreliable, breaking down after relatively short periods of operation. More critically, even these crude stabilizers required manufacturing capacity that simply didn't exist. The factories that might have produced such systems were being systematically destroyed by American bombing. The precision machine tools necessary for manufacturing gyroscope components were increasingly rare, many having been lost when facilities were hit or converted to producing more desperately needed equipment. The engineers who might have refined the designs were scattered across a collapsing war effort, working on dozens of urgent projects with inadequate resources and insufficient time. By the time Japan surrendered in August of 1945, the question of tank stabilizers had become purely academic. American armor rolling through occupied Japan included Shermans with the same gyro stabilizer system Yamamoto had tested years earlier. Some of those tanks had been in continuous combat service since Guadalcanal or Tarawa, their stabilizer systems still functioning after tens of thousands of kilometers of operation across coral atolls, jungle terrain, and volcanic islands. They represented not just military victory, but industrial and technological triumph. The lesson of the gyro stabilizer extended far beyond armored warfare tactics. It was a lesson about technological competition between nations with vastly different industrial capabilities. Japan had entered the war with equipment adequate for the enemies and conditions it expected to face. The Type 97 Chiha was a perfectly reasonable tank design for campaigns in China, where Japanese forces faced opponents with limited anti-tank capability. But war accelerates technological development, and the United States had the industrial capacity to not just produce more equipment, but to produce fundamentally better equipment. A Japanese tank crew could possess every martial virtue, courage, skill, dedication, tactical acumen. They could execute their doctrine perfectly, make no mistakes, and still die because their tank lacked a gyro stabilizer. The technology spoke in the universal language of warfare: effectiveness. The Sherman could fire accurately while moving, the Chi-Ha could not. That single difference, multiplied across thousands of engagements throughout the Pacific theater, shaped outcomes more certainly than any amount of fighting spirit. Years after the war ended, Yamamoto had a conversation with a former American tanker, a Sherman commander who had fought from Saipan through Okinawa. The American described his experience with the stabilizer system in practical, matter-of-fact terms. It wasn't perfect. It couldn't compensate for everything, especially on really rough ground or at high speeds. But it meant we could keep moving, keep the pressure on, keep shooting even while we advanced. We didn't have to stop and become sitting ducks. I think about the times we drove through Japanese defensive positions, firing continuously, and I realize the stabilizer probably saved my life more than once. Neither man mentioned that this same system had killed thousands of Japanese soldiers. Neither had to. The technology had spoken for itself. The gyro stabilizer had worked. It had provided American tankers with a capability their Japanese counterparts lacked, and Japanese forces had no effective counter beyond desperate, often suicidal, close assault tactics. The final irony was this: Japanese armor doctrine wasn't wrong. It was perfectly logical, based on the fundamental and apparently universal principle that tanks must halt to fire accurately. Generations of armor officers from multiple nations had developed tactics around this principle. German panzer theorists, Soviet tank commanders, British armor officers, they all understood and accepted this limitation. What Japanese planners had failed to anticipate was that someone would solve the problem differently. The Americans had looked at the same challenge and asked a different question. Instead of accepting that tanks must halt to fire, they asked, what if we could keep the gun stable while the tank moves? That question, and America's industrial capacity to engineer an answer, had changed armored warfare forever. The principle Yamamoto had witnessed at the Tokyo Proving Ground, that accurate fire should not require a stationary platform, eventually became fundamental to armored vehicle design worldwide. Every modern tank, from every nation, now includes stabilization systems, descended from the Sherman's gyro stabilizer. The technology has evolved. Electronic sensors have replaced mechanical gyroscopes, computer control systems have replaced Amplidyne motors, precision has improved by orders of magnitude, but the core principle remains unchanged. The gun should stay pointed at the target regardless of vehicle motion. The innovation that shocked Japanese observers in 1943 is now so standard that its absence would be unthinkable. But in the autumn of 1943, on a dusty proving ground outside Tokyo, it had been a revelation. Lieutenant Takeshi Yamamoto had arrived, expecting to confirm what everyone knew, that tanks must stop to fire accurately. He left understanding that the Americans had rewritten fundamental assumptions about armored warfare, and there was nothing, no tactical innovation, no improvement in doctrine, no amount of courage that could compensate for a gyroscope spinning at high speed, keeping a 75mm gun pointed at its target while the tank that carried it rolled forward, unstoppable, toward victory. The knowledge that came from that single morning of testing spread slowly through Japanese Armor Command, meeting resistance at every level. Staff officers who had built careers around established doctrine were reluctant to accept that their tactical frameworks had been rendered obsolete by enemy technology. Field commanders, already struggling with deteriorating strategic situations across the Pacific, had little capacity to implement sweeping doctrinal changes even if they accepted their necessity. And the general staff, facing resource shortages across every dimension of the war effort, could not authorize the industrial mobilization that developing equivalent technology would require. Some officers who read the report focused on secondary factors, seeking explanations that didn't require acknowledging fundamental technological inferiority. Perhaps American tank crews were simply better trained? Perhaps the captured Sherman had been an exceptional example? Perhaps combat reports had still been exaggerated, and the test conditions at the proving ground didn't reflect actual battlefield performance? These objections allowed them to maintain faith in existing doctrine without confronting uncomfortable truths about industrial capacity and engineering sophistication. But officers who had actually faced Shermans in combat knew better. Captain Sato's experience on Guadalcanal was replicated dozens, then hundreds of times across the Pacific theater. Japanese tank commanders maneuvered their Chiha tanks according to doctrine, selected good firing positions, halted properly, and died anyway because the enemy could shoot accurately while moving. After-action reports, the ones that survivors managed to file, described the same phenomenon repeatedly. American tanks advancing continuously, firing without pause, destroying Japanese defensive positions before defenders could respond effectively. The adaptation that Japanese forces managed was incomplete and inadequate. Some tank crews learned to position themselves in extreme ambush situations, hiding their vehicles in caves or reinforced bunkers, waiting for American armor to pass within point-blank range before firing. These tactics occasionally succeeded, particularly when Japanese tankers could achieve complete surprise and fire from concealed positions at ranges where even the Chiha's modest gun could penetrate Sherman armor. But such successes were rare exceptions. Most engagements followed the pattern established by the gyro stabilizer's capabilities. American tanks advanced, Japanese tanks died. Anti-tank gun crews received the longest-range weapons Japanese industry could provide, but even here the numbers worked against them. The Type 1 47mm anti-tank gun could, under ideal conditions, penetrate Sherman frontal armor at ranges approaching 600 meters. But ideal conditions meant a stationary target, perpendicular angle of impact, and a well-trained crew making a perfect shot. Real conditions meant shooting at moving targets, often at poor angles, while taking return fire from a tank whose 75mm gun could destroy the anti-tank position at far longer range than the 47mm gun could reliably penetrate Sherman armor. Infantry anti-tank tactics devolved into desperation. Magnetic mines, satchel charges, and lunge mines, the last being a shaped charge on a pole, designed for suicide attacks, became standard equipment for troops expected to face armor. These weapons required extraordinary courage to employ. A soldier needed to approach within meters of an enemy tank, avoid or survive its machine gun fire, and attach or thrust the explosive charge with sufficient precision to damage critical components. The gyro stabilizer made even this desperate tactic more difficult. A Sherman crew, maintaining situational awareness while advancing and firing, could engage infantry anti-tank teams before they closed to attack range. The broader strategic implications of the gyro stabilizer's lesson went largely unrecognized during the war itself. Japanese military leadership focused on immediate tactical challenges rather than the underlying industrial and technological disparities those challenges revealed. But the pattern the gyro stabilizer represented American capability to implement sophisticated engineering solutions to military problems repeated across every dimension of the Pacific War. American radar systems could detect aircraft and ships at ranges Japanese equipment couldn't match. American proximity fuzzes turned anti-aircraft artillery into area denial weapons rather than point defense systems. American logistics enabled sustained operations across vast ocean distances. American industrial capacity produced landing craft, amphibious vehicles, and specialized equipment in quantities that made island hopping feasible. Each of these advantages stemmed from the same source: an industrial base capable of precision manufacturing at unprecedented scale. Japan's industrial limitations weren't failures of will or effort. Japanese factories worked at maximum capacity throughout the war. Japanese engineers developed clever designs that extracted maximum performance from limited resources. Japanese workers labored under increasingly difficult conditions as strategic bombing destroyed facilities and disrupted supply chains. But effort alone couldn't overcome the fundamental gap in industrial sophistication and productive capacity. American factories could manufacture components requiring micron-level precision by the thousands. Japanese factories often struggled to produce even crude approximations of such components in limited quantities. The fate of Japanese tank crews in the latter part of the war reflected these limitations tragically. Young men climbed into Chiha tanks, knowing, or at least sensing, that their equipment was inadequate. They had perhaps heard rumors of the American stabilizer system from instructors who had read classified reports. Even if they hadn't heard specific details, the cumulative weight of combat reports, survivor accounts, and tactical directives made clear that Japanese armor faced systematic disadvantages. Still, they fought with the equipment they had because no alternative existed. Yamamoto continued training these crews through 1944 and into 1945. The training periods grew shorter as Japan's strategic situation deteriorated. 6 months of instruction became 3 months, then 6 weeks. The fundamentals of armor operation remained unchanged: how to operate the tank, how to maintain the vehicle, how to aim and fire the gun. But the tactical sophistication that earlier crews had received became impossible to provide. There simply wasn't time to teach advanced maneuvering, combined arms coordination, or the subtle terrain analysis that helped crews survive in combat. He watched these young crews deploy to defensive positions throughout Japan's shrinking empire. Some went to the Philippines, where American forces were already landing in strength. Others went to Iwo Jima or Okinawa, where they would face not just Shermans but also flame-throwing tanks, heavy artillery, and overwhelming air support. A few remained in the home islands, preparing for an invasion that never came. Most did not return. The casualty rates for Japanese armor crews in the war's final year approached 100% for units that saw sustained combat. The emotional weight of sending inadequately equipped soldiers into battle against a technologically superior enemy haunted Yamamoto. Military necessity demanded it. Positions had to be defended. American advances had to be contested. Every island and atoll required a garrison willing to fight. But the knowledge that these men would face Shermans whose stabilized guns could fire accurately while moving, while their own tanks would need to halt and become vulnerable, made the necessity feel like betrayal. Sometimes, in quiet moments, Yamamoto wondered about the American engineers who had developed the gyro stabilizer. What had their development process looked like? How many prototypes had they built? What problems had they encountered and overcome? The technical manuals found in the captured Sherman suggested a development program of significant scope. The documentation was thorough, professionally written, clearly the product of extensive testing and refinement. Someone had thought deeply about the problem of tank gun stabilization, had designed solutions, had tested them rigorously, had iterated until the system worked reliably enough for mass production. That reliably enough for mass production was perhaps the most impressive achievement. Building a single prototype gyro stabilizer that worked under ideal conditions would be difficult but achievable for any competent engineering team. Building a system that worked reliably after being shipped across an ocean, driven onto a beach under fire, operated continuously for weeks or months by crews with varying skill levels, maintained under field conditions with limited tools that required not just clever design, but manufacturing excellence and systematic quality control. The Americans had achieved this. Japanese industry, even at its pre-war peak, probably couldn't have. The technical reports that Japanese engineers produced after examining the captured Sherman's stabilizer system made this clear. The gyroscope bearings alone required manufacturing tolerances that Japanese precision machinery couldn't reliably achieve. The electrical components used specialized alloys and insulation materials that Japanese suppliers didn't produce in the necessary grades. The hydraulic seals needed synthetic rubber compounds that weren't available. Even if Japanese engineers had designed an equivalent system and they tried manufacturing it at scale, would have required fundamental improvements to industrial capability that couldn't be implemented during wartime. This was the deeper lesson of the gyro stabilizer. Modern warfare had become too technologically complex for determination and courage to overcome material disadvantages. A brave tank crew couldn't will their gun to stay stable while the tank moved. A skilled commander couldn't compensate through tactics for equipment that lacked capabilities the enemy possessed. Fighting spirit, which Japanese military culture elevated to near mystical importance, couldn't change the fact that a gyroscope spinning at high speed provided a stable reference that human effort couldn't replicate. The post-war period brought this lesson into sharper focus. American occupation forces brought their equipment, including Sherman tanks, into Japan. Japanese civilians and former military personnel could see firsthand the machines that had dominated Pacific battlefields. Some Shermans were even demonstrated publicly, though the technical details of systems like the gyro stabilizer remained classified. Japanese engineers who had worked on armor development during the war examined American equipment with professional interest, noting design features and manufacturing quality that their wartime industry had been unable to match. One such engineer, a man who had worked on the experimental Japanese stabilizer projects, later wrote about the experience of examining American tanks after the war. The quality of manufacture was extraordinary, he noted. Every component showed evidence of precision, machining, and careful assembly. The tolerances were tight, the materials were high grade, the finishes were professional. This wasn't prototype equipment built by specialists in a laboratory. This was mass-produced equipment built by the thousands, and yet the quality remained high. That is the mark of true industrial sophistication. The same engineer described examining a Sherman's gyro stabilizer system that had been in continuous service throughout the Pacific campaign. The gyroscope bearings showed wear but remained functional. The seals had not failed despite years of operation in tropical humidity. The electrical components, though dirty and corroded on the exterior, still functioned when power was applied. This system had been subjected to conditions that would have destroyed our experimental stabilizers within weeks, yet it remained operational. We had not just been defeated by better technology, we had been defeated by better manufacturing. Yamamoto survived the war and witnessed Japan's reconstruction. He saw Japanese industry rebuild, saw manufacturing capabilities improve, saw technological sophistication gradually approach, and then eventually exceed pre-war levels. The process took decades. The industrial base that could produce components requiring micron-level precision, that could implement systematic quality control, that could manufacture complex systems at scale. This base had to be built essentially from scratch, learning from American and European practices, investing in machine tools and training and process improvement. By the time Japan's post-war tank industry produced vehicles with sophisticated stabilization systems, the technology had evolved far beyond the Sherman's mechanical gyro stabilizer. Electronic sensors, computer control, laser range-finding, the precision that had seemed almost magical when Yamamoto first witnessed the Sherman's stabilized gun in 1943 had become merely adequate by modern standards. But the principle remained unchanged. The gun stays pointed at the target regardless of vehicle motion. The innovation that shocked Japanese observers had become so fundamental that its absence would be unthinkable. In the last years of his life, Yamamoto occasionally spoke about that morning at the Tokyo Proving Ground. He was reluctant to discuss the war generally. The defeats were painful, the losses were personal. The knowledge that so many young men had died in circumstances where courage couldn't compensate for technological disadvantage weighed heavily. But the gyro stabilizer represented something he could discuss more easily, a purely technical achievement, divorced from questions of strategy or morality or national purpose. It was simply a clever solution to a difficult engineering problem. That the solution had helped kill thousands of his countrymen was a fact he acknowledged but didn't dwell on. "I remember the sound," he said in one interview conducted decades after the war. "That high-pitched whine when they activated the stabilizer system. It was distinctive, unlike any sound our tanks made. And I remember thinking, even before I saw the shooting results, that this sound meant something significant. It meant they had built something we hadn't. And once you know your enemy has capabilities you lack, the tactical, calculations change completely." He paused, choosing his next words carefully. "People sometimes ask if we could have won if we'd had stabilizers too. But that question misunderstands what the stabilizer represented. It wasn't just one system. It was evidence of industrial capability we couldn't match. If we could have built stabilizers, we would have had the industrial base to build many other things too. The stabilizer was a symptom, not the disease. The disease was the gap in industrial sophistication between Japan and America, and no single technology could have closed that gap." The interviewer asked if knowing about the stabilizer system changed Japanese tactics. Yamamoto's response was bleak. "We tried. We revised doctrine, we changed training, we developed new tactics. But you cannot overcome a fundamental technological disadvantage through tactics alone. A tank that must stop to fire will always be vulnerable against a tank that fires while moving. We could be clever about how we positioned ourselves. We could try to achieve surprise. We could train our crews to make every shot count. But in the end, the mathematics favored the enemy. They could miss several shots and still survive to keep shooting. We needed to hit with our first shot because we might not get a second chance." The legacy of the Sherman's gyro stabilizer extends beyond its immediate tactical impact. It influenced post-war tank design worldwide. Soviet designers, examining captured American equipment after the war, developed their own stabilization systems. British, French, and eventually Chinese tank designers incorporated similar principles. The technology evolved. Electronic sensors replaced mechanical gyroscopes, computer control replaced analog systems, stabilization became more sophisticated and precise. But the fundamental principle, the innovation that American engineers achieved in the early 1940s, remained: decouple the gun from the hull's motion, maintain accuracy regardless of vehicle movement. For the soldiers who faced stabilized guns in combat, the technical evolution mattered less than the immediate tactical reality. Japanese tank crews, infantry units, defensive positions, they all faced an enemy who could shoot accurately while moving. The psychological impact was significant. A defensive position could hear a Sherman approaching and know that they would be taking accurate fire before they could respond effectively. A tank crew could maneuver for position and know that stopping to aim made them vulnerable to an enemy who didn't need to stop. The knowledge that the enemy possessed capabilities you lacked was corrosive to morale, even for well-trained and disciplined troops. The final assessment of the gyro stabilizer's impact must acknowledge both its technical brilliance and its human cost. American engineers solved a difficult problem through innovation and precision manufacturing. Their solution saved American lives by giving tank crews a decisive advantage in combat. The same solution contributed to killing thousands of Japanese soldiers who faced equipment their own industry couldn't match. Both statements are true. Both are important to understanding not just this specific technology, but the broader nature of technological competition in warfare. Lieutenant Takeshi Yamamoto climbed into a captured Sherman on a November morning in 1943, expecting to confirm conventional wisdom. He climbed out understanding that conventional wisdom had been overturned by engineering. That knowledge should have changed Japanese strategy, should have prompted a fundamental reassessment of how to fight an enemy with superior industrial capacity. But knowledge isn't power when you lack the capacity to act on it. Japan knew about the gyro stabilizer, understood its implications, and could do nothing to match it. That helplessness, more than any single battle or campaign, foreshadowed the war's ultimate outcome. The test lasted one morning. The knowledge it revealed influenced military thinking for generations. And somewhere in the mechanisms of history's verdict, in the complex accounting of why wars are won and lost, the high-pitched whine of a gyro stabilizer spinning up to operating speed deserves its place. Not because it was the most important technology of the war, it wasn't, but because it represented clearly and undeniably the advantage that precision engineering and industrial sophistication provide. In modern warfare, sometimes the laws of physics matter more than the courage of soldiers. And sometimes, one nation's ability to manufacture gyroscopes balanced to micron tolerances determines outcomes more certainly than another nation's willingness to sacrifice. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.